Hi, I'm Fernando Pereira from UFMG, and today we continue talking about 12. We shall see a few more examples of proofs in the system. First, let's prove some relations concerning the ordering between numbers. Let's start defining when a number is greater or less than or equal to another number. Would you like to do it yourself? You can start from the definitions in this figure. Here they are, the definitions. The successor of any number is always greater than 0. And if a number n is greater than another number m, then the successor of n is greater than the successor of m. That was GRT, that is, greater than. I will let you figure out how LEQ, that is, less than or equal, works. I want to know now how to prove the following. If any1 is greater than any2, then any2 is less than or equal any1. There are two ways to have the premise of the theorem. Either we have greater than via the rule GRTZ or via the rule GRTS. What if we have GRTZ? In this case, we know that any1 has the form successor of a number, and any2 is 0. So how do we conclude that any2 is less than or equal any1? That's simple. Just use the rule LEQZ, for that rule says that 0 is less than or equal to any number. If we write this proof, then we have the program on the top. However, if we try to load this script in the Twelf server, then we get an error. A coverage error, indicating that we are still missing some cases. Which cases are we missing? We can still conclude that any1 is greater than any2 using rule GRTS. But we have written the proof only for GRTZ, so that will not pass the worlds clause in this script. So how can we add in the rule GRTS to the proof? Here's the proof for GRTS. If we have that any1 is greater than any2 by GRTS, then we know that any1 is the successor of an any1 prime, and any2 is the successor of an any2 prime. Then we can apply induction on any1 prime and any2 prime to conclude that any2 prime is less than or equal any1 prime. And from that, we use LEQS to conclude that suc of any2 prime is less than or equal suc of any1 prime. And with that, we get the OK. You will see, an OK in 12 always brings some elation. And the whole script is given here on the left of the figure. Let's now look into another theorem. This time the theorem will use the notion of the double of a number. The double of a number is defined like this in the figure. So here we have the definitions of naturals, even natural numbers, and addition of naturals. How can you augment these definitions with double? This definition that we just saw. Here's the definition of double. The double of 0 is 0, and the double of the successor of any1 is the successor of the successor of any2, if any1 is the double of any2. Now, can you write this theorem in 12? The double of a number is even? Here's the declaration of the theorem. What are the two cases that we need to consider to prove this theorem? There are two ways to show that any2 is the double of any1. Either we use double Z or we use double S. At this point, would you like to stop the video and reason about the proof? I'm giving the paper style proof on the side. So first, if we conclude that any2 is the double of any1 via double Z, then we know that any1 is 0, and any2 is 0 as well. But in this case, we use even Z to show that any2 is even. And if we conclude that any2 is the double of any1 via double S, then we know that any1 has the form suc of any1 prime, and any2 has the form suc of double of any1 prime. By induction, we know that double of any1 prime is even, and using rule even S, we conclude that suc of any1 prime is even as well. You see induction as this case in the proof of EDS. It's like an implication. If even double even is true, then this fact here is also true. Let's this time prove something related to programming languages. Do you remember the big step semantics of the if-then-else evaluation that we saw in the last class, when we were talking about operational semantics? Here they are, the big step evaluation rules. And on the right, we can see them written in Twelf. At this point, perhaps you want to stop the video and then check the correspondence between the rules on paper and the rules written in Twelf. So the rules on paper are on the left side and the 12 rules are on the right side. Now let's try to show that these two programs are equivalent. If T1 then T2 else T3, and if not T1 then T3 else T2. So before we move into 12, how can we prove this correspondence? I have the proof on paper here. You can check the figure on the right. That's how we prove equivalence for one of the cases, assuming that rule B, false, was used to evaluate the if-then-else. If you want to read the proof, just go ahead and stop the video. This is the equivalence proof in 12. Notice that it does not require induction. You might try to read the script. For your convenience, the evaluation rules of the language are on the bottom right. But don't worry, we shall look into the proof in more details. Anyways, if we try to load the script, we still get a coverage error. At this point, can you figure out why is this error? Why do we get it? And what does it mean? We can try to read it more carefully. Basically, it's saying that we need to prove the theorem if eval if t is used to evaluate the if-then-else. Thus far, we are using only eval if f. So the error message tells us that we need this rule with premises x5 and x6. Premise x5 says that x1 evaluates to true, and premise x6 says that x2 evaluates to the answer of the if-then-else. Anyways, how do we move on now that we know what's missing? We can use the error message to find the proof that we want. Basically, from x6 we get that not x1 evals to false by applying x6 as the premise of eval not t. And together with x5, we have the premises for eval if f. Plugging everything back into the proof of the theorem, we get this case for if commutes t. And that's how the entire program looks like. We get an OK when we run it through the Twelf server. And with this last example, we conclude our second class about Twelf. Next time we start talking about preservation. We shall define our toy language and we demonstrate how to prove preservation for that language. Thank you.